This video is education purpose only. My name is Dr. A.N. Jagdale, Head Department of Chemistry, and today I am going to talk about Paulings valence bond theory. This topic is belong in Inorganic Chemistry, semester 3rd. Paper code is CH332. First point is Introduction to Paulings valence bond theory. Paulings valence bond theory is shortly named as VBT, that is valence bond theory. This theory deals with number 1, electronic arrangements of central metal ion and coordination number of central metal ion. It also explains the formation of coordination bond in various complexes. This theory again deals with the formation of sigma and pi bond and shape and geometry of the molecule. It also explains how electrons are donated by ligands and there is a formation of various types of bond. And lastly, this theory also explains the hybridizations of various central metal ions and magnetic properties of the complex compounds. Next point is, what are the assumptions of valence bond theory? Assumptions of valence bond theory. According to the valence bond theory, atoms combine and molecules are formed and molecules retain their original identity or entity. Atoms combine and molecules are formed according to the VBT, and when molecules are formed, they retain their identity or entity when molecule is formed. Next one is, each ligand donate lone pair of electrons and at least one lone pair of electron is donated by ligands according to the VBT. Third one is, when there is a donation of electron, sigma and pi bond formation is occur. There is a formation of coordinate bond and that coordinate bonds are either sigma bond or pi bonds. Then when coordinate bond is formed with metal and ligands, the geometry and shape of molecule is identified. Once you know the geometry and shape, from that you can determine the number of unpaired electrons. And once unpaired electrons are determined, the magnetic moment of the complex is also calculated, and for various complexes there is determination of magnetic moment by using the formula mu effective is equal to under root of n into n plus 2, where n is equal to number of unpaired electrons. Then third important point in VBT is hybridization. Definition for hybridization. The mixing of atomic orbitals, there is a distribution of their characters, and once characters are distributed, equivalent hybrid orbitals are formed having various characters and properties. It is known as hybridization. In hybridization, atomic orbitals mix, then their characters are distributed, and once characters are distributed, then equivalent hybrid orbitals are formed that gains the originality or identity of original atomic orbitals. In short, in valence bond theory, there is overlapping of atomic orbitals. When atomic orbitals are overlapped from central metal atom or ion, hybrid orbitals are formed. When hybrid orbitals are formed having unpaired electrons, they overlap with filled electrons of the ligand and there is a formation of sigma and pi bonds. When overlapping is linear, means along the axis then sigma bonding is formed, and you know that in sigma bond formation maximum overlap is there. When overlap is lateral or perpendicular to the axis, then in two space or two region their bond formation take place, and that bond is pi bond. Here sigma bond is stronger bond as compared to the pi bond. Reason is that in sigma bond there is a maximum overlap, and in pi bond that overlapping divide into two region. One is above the axis and second is below the axis, and when such type of overlapping is occur, then electron density is divided into two region, and when electrons are divided, here maximum overlapping is not there. Actually, according to the valence bond theory VBT, when there is a formation of coordinate bond, then electron density is gathered in between the two nuclei. Electron densities gather in two nuclei, and various types of hybrid orbitals are formed by central metal atom or ion in hybridization, and these hybrid orbitals are here sp, then sp2, then sp3, then dsp2, then dsp3, then sp3d, then d2, sp3, and d3, sp3. All these are the types of hybrid orbitals in hybridization. Here sp means one s orbital and one p orbital overlaps, and there is a formation of linear hybrid orbitals. It is known as sp hybrid, and hybridization is sp hybridization. In sp2 hybridization, 1s orbital combined with 2p orbitals. You know there are three types of p orbitals, px, py and pz. Out of that, here 1s orbital and 2p orbitals combine, and there is a formation of sp2 hybrid orbitals, and that is sp2 hybridization. In sp3 hybridization, 1s orbital and 3p orbitals px, py and pz combine, and this is the sp3 hybridization. Here sp2 hybridization is triangular or trigonal, sp3 is a tetrahedral. Then in dsp2 hybridization, you know there are 5d orbitals, dxy, dxz, dyz, dx square minus y square and dz square, and out of that 1d orbital, then 1s orbital and 2p orbitals combine, and there is a formation of dsp2 hybridization. It is known as square planar hybridization. Then dsp3 hybridization, 1d orbital, 1s orbital and 3p orbitals px, py and pz combine, and there is a formation of dsp3 hybridization. This is a trigonal bipyramidal. This hybridization has a set square planar. This is a tetrahedral, this is trigonal, and this is a linear one. If you go to the next sp3d, 1s orbital, then 3p orbitals and 1d orbitals combine, means there is the overlapping of 1d orbital, 1s orbital and 3p orbitals, and sp3d hybrid orbitals are formed, and it is known as sp3d hybridization. And shape of that complex hybridization means complex compound is square pyramidal. Here d2 sp3 hybridization, 2d orbitals, then 1s orbital and 3p orbitals combine, and there is a formation of d2 sp3 hybrid orbitals. Here all that 6 hybrid orbitals are equivalent, and it has octahedral shape. Then next one is d3 sp3 hybridization, 3d orbitals, then 1s orbital and 3p orbitals px, py and pz combine, and there is a formation of here 7 equivalent hybrid orbitals. Out of that 3 sp3 are at the regular corner, means equivalent. One lobe is above the plane and second is below the plane, that for the what? Pentagonal structure, and that is d3 sp3 hybridization. and the shape of this molecule is pentagonal bipyramidal. Means geometrical shapes for this hybridization, this is the linear, this is trigonal, this is tetrahedral, this is square planar, this is trigonal, then bipyramidal, this is here square pyramidal, this is octahedral, and this is pentagonal bipyramidal, and these are the various type of hybridization and their respective shapes. Then some types of hybridization, then geometries of that molecules, then geometrical shapes, and examples of various types of hybridization. Then first one is serial number, that is suppose 1, then geometry or hybridization is represented here. Hybridization that is supposed to the SP, then geometrical shape, here it is a linear, then actual geometry of that complex, that is metal is at the center position and ligands are linearly arranged, and example is here suppose there is a formation of Ag NS3 twice plus. Then second example is hybridization is sp2. Here geometrical shape is trigonal. In trigonal molecule there is a regular triangle or equilateral triangle. In that equilateral triangle, metal is at the center position and ligands are at the 3 regular corners of the triangle. Here example is suppose there is a formation of HgI3 here 2 minus. Then third example is suppose there is a formation of sp3 hybridization. It is a tetrahedral. In tetrahedral arrangement, metal is at the center position and 4 ligands are at the regular corners of the tetrahedron. At the center position, there is metal ion or atom, and this type of structure is formed. Example is suppose there is a formation of MnCl4 2 minus complex ion. Then next example is number 4. There is a formation of dsp2 hybridization. This dsp2 hybridization is square planar hybridization. There is a square. At the center position there is a metal and 4 ligands are at the regular corners of this square. And example is suppose there is a formation of NiCN4 here 2 minus complex ion. Then fifth example is suppose there is a formation of dsp3 hybridization. It is known as trigonal bipyramidal hybridization. In trigonal bipyramidal hybridization, there is a regular triangle. At the center position, there is a metal ion or metal. Then one ligand is above the plane and second is below the plane, and 5 ligands are there, shape of that molecule is trigonal bipyramidal. Example is, suppose there is a formation of FeCO5 complex ion. In that sp3 hybridization, it may be represented as sp3 dehybridization. It is known as square pyramidal, and in square pyramidal there is a square, metal is at the center position and one ligand is above the plane, and here remaining 4 ligands are at the regular corner of the square. The shape of the molecule is square with a pyramid. One pyramid is there, that is square pyramidal, and example is here Sb, then F5 2-. Then next hybridization is here D2sp3 hybridization. That hybridization is known as, here supposed to the what, number 6 is D2sp3 hybridization. It is known as octahedral hybridization. This is known as octahedral hybridization. In octahedral hybridization, there is octahedral structure. Then metal is at the center position. Then 4 ligands are at the regular corners of the square. Then 1 ligand is above the plane and second is below the plane. Then this octahedral structure is represented like this. This is the octahedral arrangement of the complex compound. Here example is, suppose there is a formation of FeCN6 3- complex ions. All these are the various types of hybridizations. Then their arrangements means geometrical shapes, actual geometry of that molecules, and these are the respective examples of various types of coordination compound. See again, here number 1 is hybridization is sp hybridization. In sp hybridization, 1s orbital and 1p orbitals overlap, and there is a formation of sp hybrid orbitals. These hybrid orbitals are formed by these silver Ag+ ions. Then ligand of NH3, 2 NH3 ligands are there. Each donate lone pair of electron, means 1 lone pair of electron, and 2 coordinate bonds are formed, and that coordination compound has geometrical shape as a linear. Linear means straight line, and this is the straight line. In this complex compound, metal is at the center position and 2 ligands are at the 2 ends. Here is 1 ligand and here is second ligand. If you take the example of AgNH3 twice plus, here Ag is at the center position, 1 NH3 ligand is here and second NH3 ligand is here, and charge on Ag is plus. Then second example is sp2 hybridization. In sp2 hybridization, 1s orbital and 2p orbitals combine, and there is a formation of 3 hybrid orbitals by mercury metal ion, that is at the ground state or center position. When these 3 sp3 hybrid orbitals are formed, they overlaps with ligand iodine unpaired electron hybrid or unpaired electron orbitals, and there is a formation of here 3 coordinate bond. The shape of that geometrical shape is a trigonal, means a regular triangle is there. This is equilateral triangle. In this equilateral triangle, metal is at the center position, and to the regular corner of the equilateral triangle 3 ligands are present, and these are the 3 iodine ligands, and metal ion is mercury here, and this is the example for sp2 hybridization HgI3 2-. Third example is 1s orbital and 3p orbitals combine. These 3p orbitals are px, py and pz, and there is a formation of equivalent 4 sp3 hybrid orbitals. The geometrical shape of that hybrid orbital is tetrahedral, and this is the tetrahedral shape. In tetrahedral shape, here metal is at the center position. Example is MnCl4 2-. In this complex, manganese is at the center position. 4 chloride ligands are at the regular corners of the tetrahedron, and charge on that complex is 2-, because here 4 negative ligands are there. Charge on manganese is Mn2+, and this is the structure, and hybridization is sp2 hybridization. Then dsp2 hybridization. In dsp2 hybridization, 1d orbital, then 1s orbital and 2p orbitals combine, and there is a formation of 4 equivalent hybrid orbitals. These 4 equivalent hybrid orbitals, suppose example is NiCN4 2-. This forms 4 equivalent hybrid orbitals, and 4 ligands donate 8 electrons, and respective coordinate bonds are formed there, and the shape of that molecule is square planar. This is the complex ion. Metal nickel is at the center position having charge N2+, nickel 2+, and 4 here cyanide ligands are at the regular corners of the square, and this is the example for the square planar hybridization. Next one is dsp3 hybridization. 1d orbital, 1s orbital and 3p orbitals combine, and there is a formation of 5 hybrid orbitals. Out of that, 3 hybrid orbitals are equivalent. One lobe is above the below and second is above and second is below, and this type of structure is formed. It is known as trigonal bipyramidal structure, and example is FeCO5. In this complex compound, at the center position iron metal atom is present. Then to the regular corner of the triangle, 3 carbonyl ligands are there. One carbonyl ligand is above the plane and second carbonyl ligand is below the plane, and therefore shape of this molecule is trigonal bipyramidal. Then next one is sp3d. It is again a square pyramidal hybridization. It is not bipyramidal, but it is square pyramidal. Here is a square and one ligand is above the plane and metal is at the center position. Here SbF5 2- is an example for this square pyramidal structure. Here Sb is at the center position. Then 4 ligands are at the regular corners of fluoride of a square and one is above the plane. Therefore it is known as a square pyramidal shape, and this is the example and this is the structure for square pyramidal. Then last one is D2sp3 hybridization. 2d orbitals, 1s orbitals and 3p orbitals. In FeCN6 3-, here iron is at the center position. At a ground state there is overlapping of these 2d orbitals, 1s orbitals and 3p orbitals, and there is a formation of equivalent set of 6 hybrid orbitals, and the shape of that molecule is octahedral, and this is the example FeCN6 3-. In this complex, iron is at the center position and 6 cyanide ligands are to the regular corner of the octahedron and 6 sigma bonds are formed, and here FeCN6 3- is example of octahedral complex, and all these are the types of hybridization: sp hybridization, sp2 hybridization, sp3 hybridization, dsp2 hybridization, dsp3 hybridization, sp3d, then d2sp3. All these are the types of hybridization. These are the corresponding examples of AgNH3 twice plus, HgI3 2-, MnCl4 2-, NiCN4 2-, FeCO5, then Sb5 2-, and this is the last example for the D2sp3 hybridization, that is FeCN63-, and their shapes are, first one as sp has linear shape, sp2 trigonal, sp3 tetrahedral, then dsp2 square planar, then dsp3 that is trigonal bipyramidal, then next one is sp3d, it is square pyramidal, and last one is octahedral, that is metal at the center position, and FeCN63- is formed there, and these are the examples of hybridization. From these examples and their corresponding ground state box diagrams, you can determine or find out the number of unpaired electrons, and from that number of unpaired electrons, and using the magnetic moment as formula to calculate the magnetic moment in Bohr magneton, you can find out the magnetic properties. Means next point is magnetic properties of coordination compounds according to the valence bond theory or VBT. According to the valence bond theory or VBT. Next point is magnetic properties. Number one is paramagnetic. Second is diamagnetic. Listen, what is meant by paramagnetic compound? When coordination compound possesses unpaired electron or electrons, these compounds are known as paramagnetic. When unpaired electrons are absent or all electrons are present, then that compound is known as diamagnetic. There are again two more magnetic properties. One is ferromagnetic. Ferromagnetic means excessive paramagnetic property, means number of unpaired electrons are more there. And in antiferromagnetic property, when electrons moves randomly or not in one direction or arrangement is random, it is called as antiferromagnetic compound. For T.Y.B.Sc, these two properties are important. One is paramagnetic and second is diamagnetic. Again listen, paramagnetic means number of presence of unpaired electrons, and diamagnetic means all electrons are paired. And magnetic moment is determined by using formula here mu effective is equal to under root of n into n plus 2, where n is equal to number of unpaired electrons, and that property is measured in Bohr magneton BOHR, and short form is represented as Bm. Short form is represented as Bm. If you consider the D block elements, then in D block elements, suppose number of unpaired electron is equal to 1. At that time, by using this formula, mu effective means magnetic moment of that complex or complex ion is determined by formula mu effective is equal to under root of n into n plus 2, where n is equal to number of unpaired electron, where n is equal to suppose 1. At that time it is equal to under root 1 into 1 plus 2, that is equal to under root 3, and under root of 3 is equal to 1.78 Bm. Means when n is equal to 1, number of unpaired electron is equal to 1. At that time magnetic moment by using VBT, that is mu effective formula, under root of n into n plus 2, that value is equal to 1.78. Then when n is equal to 2, then here is again this value is equal to 2, here 2, here that is under root of 8, and that value is equal to here 2.83. Then like that, when n is equal to 3, then that value is equal to 3.88. Then when n is equal to 4, that value is equal to again here 83. Then 4 point here that is 88, 4.90, and when n is equal to 5, that value is equal to 5.92 bm. And these are the corresponding respective values for the unpaired electrons, and these values are determined by the equation where mu effective is equal to under root of n into n plus 2, where n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5, and these values are determined in the unit Bohr magneton represented as Bm, and equation is equal to mu effective is equal to under root of n into n plus 2, where n is equal to number of unpaired electron. That means by VBT valence bond theory, it is also known as Paulings valence bond theory, you can calculate the magnetic moment of that complex from the number of unpaired electrons. Then from the hybrid orbitals and overlapping atomic orbitals, you can find out how many bonds are formed, means coordination number of central metal ion, then shape of that molecule, then geometry of that molecule, then number of unpaired electrons, and how electronic structure or arrangement is there around the central metal atom, and that is the introductory part, and hybridization for the what? Valence bond theory VBT, and from VBT you can again determine the magnetic moment, either paramagnetic or diamagnetic. Paramagnetic means presence of unpaired electrons, diamagnetic means absence of unpaired electrons, or all electrons are paired. And two more properties are there. One is ferromagnetic, means excessive, here unpaired electrons are there. Antiferromagnetic means random movement of electron is there, and from this you can determine the various structures like octahedral complex, then tetrahedral complex, then square planar complex, then trigonal bipyramidal complex. Their magnetic moment means number of unpaired electrons, geometrical shapes, then geometry of the molecule, and a box diagram for the various complex compound and complex ion. And that is enough for the introduction to the valence bond theory, hybridization and magnetic property. Thank you.